Hello, welcome to another problem session. I was gone for a couple of days, but I will start again. So today we have a interesting problem, kind of a standard problem. The name of this arrangement is called Ballistic Pendulum, and we basically what we have is a large block, a pendulum which is a large mass here. This is the pendulum here. This is hanging, it's at rest, and a small mass such as bullet. So this is M and this is capital M, with some speed which is comes and embeds itself, and it hits it horizontally. So this is horizontal. That's what and then this bullet will become part of this thing. It will just embed itself. So this is, say, this situation is t equal to 0, and then the whole structure will swing, and then everything will come to rest. At that point, this angle is theta, and that's the angle we're supposed to find out. So this is some time t equals to t, and of course it's going to start to swing like a regular pendulum at that point onward. Okay, we're not concerned about what happens afterwards, but we need to figure out this theta, and this length all the way to the center of mass of this whole thing is L. It says length L. It kind of implies this is the length L, but I'm going to assume that length L is to the center of mass. This is L. So this is a standard way of writing this problem, but it has a little ambiguity here, right? Because physics I'm going to use the physics of center of mass later on. So this I would say this is the center of mass. So this is the center of mass where the bullet and everything is. Okay. So I know if we knew the speed here at this point, if I knew this after impact, if I knew the speed after impact, VA, so VA is speed immediately after impact. So let's call it t. Let's call it time t equal to 0 plus, and let's call this time 0 minus, before the impact, and this is after the impact. If we knew this, if we knew this, then you know from here to here, by comparing energy conservation, then by energy conservation, between t equals to 0 plus and t equals to t, we will get theta. So here is how, if we knew it. So that's we start from the end rather than the beginning. So if we knew this, then energy here has to be equal to energy there, right? So that will be energy at t equal to 0 plus must be equal to energy at t equals to t. And so that energy is going to be, let's see, this is the level at which we're going to call it potential energy 0 reference. Anything above that is positive potential energy, anything below that is negative potential energy. So we are going to say over here, right now at this time 0 plus, potential energy is 0, so it's all kinetic energy. So you have a half m plus big M VA square plus 0. That's the potential energy. Over here V is 0, so no kinetic energy, it's all potential energy. But I need to figure out how much this height is. Well, if you look at this triangle, if this is L, if all the way to center of mass, that's why remember I was telling you the center of mass earlier. This is the reason. If this is L, then this from here to here, this side will be L cosine theta. But from here to here, all the way will be L. So L minus L cosine theta. So kinetic energy is 0. And then we have M plus big M G times L minus L cosine theta. So you can see that if I know this, then I can figure out theta in terms of G and L and things like that. So this one simplifies a little bit. Mass is cancels out, and you can rewrite everything, but I'm going to just leave it here. Then because I'm going to come back to it, I need to have another way to get this so that I can plug in here and get the angle theta here, right? So that other one will be between t equal to 0 and t equal to 0 plus. Now I'm across the impact. So second piece of information I'm going to use is across impact. And you probably already guessed it, this will be a momentum conservation. And momentum is a vector, but that means we could write x and y and z, but here is very simple, right? So if you consider this to be positive x-axis direction, then I'm going to get px net, which is like a px bullet plus px block. So px net, I'm going to get px net at t equal to 0 minus must be equal to px net t equal to 0 plus. So this is what's going to happen, right? Now for px equals, this one is very easy. Left side is easy. Left side is easy because we have this guy is at rest, block is at rest, block that gives me 0, and this gives me positive mv. So this is m little v plus 0. But after the impact, both of them, block as well as bullet, is moving at va together. They're moving at that speed, right? So I have mva plus big mva, both together moving together. So this will give me va, and I can plug in there and I get theta. So let's work that out. So va is going to be m over m plus mv, and plug in there. So I get half mv over m plus m square is equal to GL 1 minus cosine theta. So now I'm going to solve for theta. It's very easy now, right? I'm going to put this on the other side, and then bring subtract 1 from both sides, and so cosine theta will turn out to be 1 minus 1 over 2 GL mv over m plus m square, and so theta will be our cosine of this stuff. Okay, so make sure that everything I'm just making sure that I didn't make any boo-boo around here, some problems, mistake. There's very few algebra here. It's possible I messed up, but looks correct. You can see this is speed square, so, and g length square over time square, and this length square over time square. So this is unitless as it should be. So okay. As always, you should go back after you solve the problem to identify what steps you had to take in interpreting the problem, as well as carrying out the solution. Okay, so as far as I can tell, the standard way of writing this problem is like hanging by a mass string length L. Kind of a little bit deceptive in the sense that if I don't use the center of mass, I would probably misunderstand a little bit of it. Suppose I didn't do CM, okay? So suppose I didn't do CM. So CM is over here and goes over here. So if you look at this is the one that went to potential energy. So let's use this as LCM, and so this will be LCM, and this is theta, and this is now L. So I'm just following the way the problem is usually stated and what's wrong with it, right? So this will be L 1 minus LCM cosine theta. And so if I work with this distance instead, this will be big L 1 minus cosine theta. So when I wrote down conservation of energy, so this was T equals to T, and at this point was VA, T equal to 0 plus. Conservation of energy, I would be, left side will be the same, VA square, but the right side will be 0 or plus for this kinetic energy, and this would be in actuality it is mg LCM 1 minus cosine theta. This is in actuality, which we called L before. So because LCM is greater than L given, you can see that there will be a mistake, right? For instance, so the answer would be a little different. You have a cosine theta is 1 minus, let me see, look up the answer. So answer will be LCM here, right? And I earlier I used L for it, but it should be LCM. So cosine theta will be actually should have been this, but people write it as if L given or L string given is L string. L string is not equal to LCM. So there's a little bit of mistake here. We make, and that's a very common thing that happens, but you should always be aware that whenever we write something like this, this is how much the center of mass has actually been lifted. It's not about whether the top of the string has been lifted or whatever, okay? So you should stay on the physics side, and then you'll be able to recognize the assumptions you're making. Sometimes the assumptions are okay. If the block is very massive and not very high density, then this and the string is very long compared to the size of the block, then this is all probably very close, no big deal. So the assumption may be, you can say, assuming L string is much bigger than the size of the block. Okay, that's one of the assumptions I would say, right? Okay, that should kind of clarify some of the things we worked on today. So we'll talk to you later. Bye.